All right, here are just some general reminders about projectile motion. So projectile motion is really just kinematics in 2 dimensions. So we're launching something with a velocity v naught at an angle of theta. And what that means is that based on vectors, what we're really doing is launching at some horizontal velocity, this to the right, and then some vertical velocity up. And we know how to break down those vectors. We know that horizontally there's no acceleration because we understand gravity. You know, gravity is only down, right? The force of gravity is mg, the acceleration due to gravity is g, and it's only down. And so horizontally, our position equation is just original horizontal velocity times time, no acceleration. Our vertical position, well, it looks like it just did in the last chapter. If we were just throwing up a ball from a building, right? There's the building height, there's the vertical velocity, and there's gravity's effect. And then vertical velocity, of course, is our original vertical velocity minus gt, right? It's the same thing. Acceleration times time gives you the change in velocity. We're going to subtract it because it's down. Now, could there be a minus sign here? Sure, right? If you threw something, you know, to the right, but you threw it down, well, then that would have to be a negative. Okay, so again, those are just our standard position and velocity equations, just like Unit 1. They just now are in component form because we're in 2D, right? We're with a vector. We talked about the target equation, and it's really just like the v squared equation in the first unit, that this equation is easily derived, right? This is the no time equation for 2D stuff. And so we have a ball here, and we're gonna launch it at a certain velocity, v naught, and we want it to cover a certain distance and to be at a certain height, right? We want to hit something. And so this target equation generally solves for the angle. So you're going to graph the height you want to be at, and you're going to graph this side of the equation where x isn't the variable, right? X is the known number, and theta is the actual variable, and you're going to solve for the intersection. The graph on that usually looks, you know, something like, and it comes down like this, and then you're going to graph another one, and you're going to find these intersection points. And those are the 2 different angles that you can be here, launch it at that speed, and have it travel that distance and be at that height. That's not something you have to memorize. It's very easily derived. All you're doing is taking x and saying, I want to be at a certain position at a certain time, so you solve for t, right? That equation then becomes t equals x over v naught cosine theta. And all you're doing is taking that time, the time at which you've traveled a horizontal distance x, and you're plugging in for time here and here. And so then you're deciding that, okay, I'm going to be at this horizontal position at a specific time, and I want to be at that specific height. And then when you simplify it algebraically, you just get this equation, and you're going to find the angle that makes that happen. The range equation, again, the real range equation, of course, is just this guy, right? That's the real range equation. That always tells you that horizontally, your distance horizontally is just how fast you're moving horizontally times time. That makes sense. But if you manipulate that a little bit and we use some symmetry, we can show that the flight time is actually double the time at max height. The max height corresponds to when the vertical velocity is 0, and you do just a quick substitution in for t, then you get this equation, which is nice because this tells us that if we throw it so fast at a certain angle, I can tell you exactly how far it's going to go. And I don't really care about the time on that one either. Other ideas, you know, I asked you, you know, when is it going to hit the ground, right? We launch something from a building and you want to know information. We're going to want to know that point, right? All we have to do is set y equal to 0. So look at your standard position equation, let y be 0, and graph that quadratic and find that x-intercept, right, which will be the flight time. You can find max height on your calculator. Certainly that's your building height. You can do all sorts of things, right? But hitting the ground does mean y equals 0. If 2 things are kind of moving, so this is like the shoot the monkey problem. There's a problem on the review like it where I want to have 2 objects collide. Just remember, start the problem by the definition of what it means to collide. I want the 2 objects to have when they have the same horizontal position, I need them to be at the same height. Again, these match up at the exact same time. So figure out the time it takes for this to happen, and then just set their y values equal at that moment in time. We do know that max height corresponds to a vertical velocity of 0, not a velocity of 0, a vertical velocity of 0, and that time would specifically be this, and that makes sense in our head. This is just vertical velocity thrown up. That's dividing by gravity. Remember, gravity is going to take away 9.8 meters per second every second, and that just figures out how long it takes gravity to take away the vertical velocity. So that's the time at max height, right? T max. Not the maximum time, but the time it's at a max height. Then we have problems where we can like shoot something, except we're not going to land on a level surface. Now we're going to shoot something and we're going to land on a ramp. So I think there's a skiing problem where you're coming in as the skier and then you're going to land something like that. So you hit this jump right here, and as the skier then you land on a ramp. And I just want to remind you that whether it's uphill or downhill landing, that the X and the Y variables are related, right? You know that there is some, again, this angle here this is like the launch angle, so there's like a theta there, but then the ramp angle is some different angle, we'll call it phi, and that how far you go, you know, if let's say you got shot here, right, and then you land on the ramp, how far you go horizontally to your vertical distance are related by this angle here, right? Tangent of that angle phi is y over x, and so x tan phi equals y. It gives you the ability to relate those two variables. So if you have an equation, you look at it like maybe you have this target equation, like, oh my gosh, I don't know, I have I have two variables, but you don't really, because y and x on the ramp are related based on that angle. Finding a final velocity, like in this case, if I wanted to find the final velocity that it struck the ground with, remember it's a vector, and so what you need to know to be able to find the magnitude and angle of that vector is you got to know how fast you're moving horizontally, which didn't change, that's just v naught cosine theta, and then your vertical velocity at that moment. But if you know the time there, well then of course you can just plug in to the velocity equation and find out how fast you're moving vertically there, how fast you're moving horizontally there, and then you can do Pythagorean theorem and inverse tangent to find the magnitude and the angle. Again, final velocity, draw the triangle, find the two pieces, do Pythagorean theorem and inverse tangent. And then there could be like a lab question where I give you information like, hey, I launched, you know, a ball and it did this. And in the lab, I think we went through and we launched it horizontally, we launched it vertically, and then we launched it at an angle. And it could have been symmetric or not symmetric, it doesn't matter. You know, you have the ability, if I tell you some information, you know, in the lab, your goal was to find the V naught of the launcher, and then once you knew V naught, then you could hit a target. And when I mean by hit a target, you could actually find the angle appropriately, right? That's what we did for the Dragon, right? We did some experiments, took some data and found enough information to find V naught, and then with V naught, then we were allowed to, you know, we figured out what angle we could do to hit the Dragon, right? This is a pretty good summary of like all the different situations, but realistically, you really just have these three equations, and you're doing them in as many different orders as possible. The easiest case is like this one, where I give you V naught, I give you the angle, and I give you the building height, and then I ask you a whole bunch of questions. But I wouldn't have to, right? I could give you how far it went horizontally and the max height, and you should then be able to find the angle and the time and the initial velocity. Or like the target situation, I could give you the velocity, the height, and the distance I want it to go, and you have to be able to find the angle. You should then also be able to find the time it takes. You should be able to figure out, you know, if it hits this target here, how fast is it moving when it hits the target? All of those things you need to be able to do. You know, we did examples of the ramp. I think we did more downhill, but uphill, it's the same thing. But downhill, like the skier one, where you get launched and you know you're flying down, and the picture would look something like this. Make sure there are two different angles, right? There's the launch angle, which breaks down the velocity like this, and then there's the actual ramp angle, and that ramp angle allows you to relate X and Y. Okay, so hopefully this video helps. I will make a video, you know, walking through the actual review, but this should be a pretty good summary.